So I'm going to tell you something about T-structures on the derived category of G equivariant coherent sheaves on the Steinberg variety. And the two parts of this talk, I'm going to introduce the categories I will care about, and I will talk about the equivalences and T-structures. Okay. So let's start with the first category, which is, well, I mean, this one. And everything that's going to happen will happen over field F, which is going to be algebraically closed and of positive characteristic. Now, G is going to be a simple algebraic group over F. And I want the Coxeter number to be larger than the characteristic. H is a Coxeter number. Just a small reminder is that if G is equal to SLN, then H is equal to N. So I don't want my P to be too small. Okay?
Sorry, I think you want the inequality the other way.
If P is larger than H, fine.
Okay. So now, of course, small g is going to be the Lie algebra of G. And I want to consider the flag variety, which I will denote by curly B. And I can think about this as Borel subalgebras inside of G. And then I can consider its Springer resolution, which I will call curly N tilde. By definition, it consists of pairs X and B, where B is a Borel, meaning an element of the flag variety, and X lies in the derived subalgebra of B. Okay, it's Springer resolution. Now then I want a related variety called Grothendieck resolution, and denoted by G tilde. A similar definition, but now I want X to lie in the Borel, not just the derived subalgebra. In particular, this thing projects onto the Cartan subalgebra of G, and N tilde is a fiber over 0. And notice that both of these guys map into G just by forgetting the Borel subalgebra. In particular, I can consider the fiber product. And this is the Steinberg variety. So maps G, and this gives rise to Steinberg, which is a fiber product of G tilde and N tilde over B, which means that it consists of triples. The first element is still X, an element of G. And then I have two Borels, B1 and B2, and I want X to be contained in B1 and in the derived subalgebra of B2. Okay. And what it is, it's a fairly nice variety. It's a complete intersection, and it's reduced. Okay. And now notice that the group G acts on the Steinberg. So what I can do, well, I could try to play with this a bit. No, I shouldn't. What you can do, you can consider the bounded derived category of equivariant coherent shifts on the Steinberg. And up to a little twist, this is one of the categories that I'm going to care about. And what I actually want to do, I want to produce some derived equivalences between this category over here and some classical representation theoretic categories associated to semi-simple algebras. And I want to describe the corresponding T structures that I get on this category. Okay, that's a goal. Are there any questions?
Yeah, could you repeat what you said, but you didn't try? How to describe ST kind of explicitly?
So I will have some classical representation theoretic categories that I'm going to explain in a minute. And I'm going to prove, I'm going to say that the derived categories are equivalent to this. Moreover, I'm going to explain where, in some terms, where the corresponding abelian categories go. Okay. No questions?
Sorry, isn't this non-reduced?
No, this is reduced.
But so, I mean, over n, p tilde has this non-reduced, right? So isn't this different from n tilde cross n tilde over n?
It's different from n tilde cross n tilde over g, which is a derived scheme, honestly. And this is a genuine scheme.
But you're saying
it's
this
reduced.
is the same as n tilde cross n tilde over n.
As a set.
But it's not over n. Or you're saying over n, it still has some derived.
When I was young, people explained to me that these questions are answered by let's discuss this later. Okay, I promised you some classical representation theoretic categories, and the first of them is going to be category O. Okay. So let me fix a barrel B inside of G, a group. And my category O is going to be, well, let me write this in words, strongly be equivariant, finitely generated G modules. So let me explain what this means in more detail. So my O consists of M, which are modules over G, and rational representations of B. And I want them to be subject to the following conditions. M is fine. I want them to be finitely generated. I want the action of G on M, the action map, to be equivariant. That's usually called weak equivariance. And I want also strong equivariance, which says that the differential of the B action on M coincides with the action of B sitting as a subalgebra of G. So these are the conditions, and of course morphisms in this category are both G and B linear maps. So just a side remark, you may be familiar with this object in characteristic 0, in which case the presence of this action is a condition, but in characteristic P this needs to be an additional structure.
Which condition is missing?
No, I mean there are no missing conditions. So in characteristic zero, you can state it entirely in terms of the Lie algebra,
Ah,
and then the integrability to B will be a condition.
yeah, it's a little
Here
bit
it's an additional
like
structure.
Harish-Chandra modules, right?
Hmm?
It's a little bit like Harish-Chandra modules.
Yeah. Okay. Let me give you an example of an object. And it's a Varma model. So if I pick lambda, which is a character of the group B, I can form the corresponding representation. And then I can define the object delta lambda, which is going to be the induced module from u of b to u of g from f lambda. This has an A-shell Lie algebra action. It also has an A-shell action of the group B. Okay, and it's an object in category O. Now, that's not quite a category that I want. I want to care about a certain direct summand in this category, and it's so-called principal block. To define this, let's recall that we still have a Harish-Chandra isomorphism between G invariants in the universal enveloping algebra and W invariants in the dual of the Cartan under the dotted action of the while group. Okay. That's a row shifted action. That's Harish-Chandra isomorphism. And then you can show that the center acts on every object from category O locally finitely, so you can write the block decomposition as usual. So the action of U of G, the center of U, the G invariance in U of G. Object in O gives rise to decomposition of O into blocks. And I'm interested in the principal block, where the center acts with the same eigenvalue as on the trivial representation. Equivalently, I can say that this is a span of objects of the following form. Varma modules with highest weight x dot 0, and I need to explain what x is. So x runs over the affine while group. Well, W affine is W semi-direct with the root lattice. Lambda. And so how does, well, I mean, W still acts by the dot action, and the root lattice acts by the p-rescaled action. So if I take lambda in lambda, well, maybe I should write mu in lambda, then it gives me an element in the affine while group, and T sub mu applied to lambda is lambda plus p mu. Okay. So again, you may be familiar with the classical characteristic zero story. In classical characteristic zero story, you take all Varmas whose highest weights are in the same W orbit as the weight of the trivial representation, which is 0. And now you do the same, but you consider highest weights modulo P.
But
This
when you
this
write
comes
P,
from.
you mean shifted action of the
Yeah,
while
yeah.
group.
So it's
But
always
here-
shifted action.
But here dot is
Well, I mean, it's for elements of the lattice. There is nothing to shift. Well, you can write plus minus rho, and that's not going to change anything. Okay. So that's one of the representation theoretic categories that I'm going to care about. Another category that I'm going to care about is a category of Harish-Chandra bimodules. So let me introduce the shorthand. Small u is going to denote the universal enveloping algebra. And then I will need its quotient, so-called trivial central reduction. Let me write it here. So I take 0 inside of H dual, and I consider the corresponding maximal ideal M0 inside of this ring of W invariants, which is also the same as the G invariance in the universal enveloping algebra. And so I can consider the quotient, which I will call U0, which is going to be the quotient of U by the ideal generated by M0. So this guy is central, and therefore this is a two-sided ideal. So what I get is an algebra.
Right. Since now we actually do have to be careful about the row shifts. This is the maximal ideal that kills the trivial.
Yep. So good to have somebody who cares about row shifts. And so, again, I first introduce a somewhat larger category than what I want to deal with. This is going to be a category which I'm going to denote by U0 opposite mod G. And in English, this is going to be weakly equivariant, weakly G equivariant, right modules of this quotient U0. Okay? So these are modules over U0 and modules over G, and the actions are compatible in the way that the multiplication map is equivalent. Okay? So now, an observation is that on such a module, I have a canonical left action of U. How does it come to be? So let me take an object X inside of here. And then I claim that U, the universal enveloping algebra X on X, this is a unique action which commutes with U0 in such a way that the operator adjoint of X coincides with image of X under the differential of the G action and X here is an arbitrary element of my Lie algebra. So this are, if you wish, these are weakly equivariant right modules which become strongly equivariant as bimodules. And for people who are familiar with Harish-Chandra bimodules in characteristic 0, you again know that on such a bimodule, the adjoint action of the Lie algebra integrates to an action of G. There it's a property, here it must be a structure. Now, similarly to what I had before, I want a principal block, and which is defined in the same way. So the action of the G invariant part of U from the left gives a block decomposition of this category of equivariant right modules, and then I can consider the principal block. Which I'm going to denote HC of U with superscript 0 after the bracket, with subscript 0 after the bracket. So this is one category I'm going to care about, this is another category I'm going to care about. And so somehow the goal is to relate the derived categories to this one.
Wow. In characteristic 0, those are more or less equivalent categories, right?
These are more or less they're just equivalent as abelian categories, and this should be replaced by equivariant right D modules on the black variety.
Equivalent.
Yeah. G equivariant right D modules.
And in this case, they are not equivalent.
In this case, everything is equivariant.
No, I mean equivalent. Categories are not
The
equivalent.
derived categories are equivalent, the abelian categories are not. Okay, so let me just give you a preliminary result, and then I'm going to make it more precise and tell you something about a proof. In the second part of the talk, so the preliminary result is the following equivalence of derived categories. So dB of O principal is equivalent to dB of HC U0 is equivalent to dB of G Steinberg. But now I need to do a little twist, and this is going to be Frobenius twist. I'm going to put the superscript 1 here and here. So what does this mean? So this 1 is a Frobenius twist. So what is this about? These are these are categories over the field F. Okay, they have a linear structure, and this, for example, these two are schemes over F. So what I'm going to do, I'm going to twist this Frobenius structure by Frobenius to -1. And this twist is to make sure that the map, which sends x to power p, now becomes linear instead of twisted linear. Okay? So that's just some accounting device for the F linear structures. You don't need to care about it that much. All right. Any more questions?
How does it change the abelian categories themselves when you write the Frobenius twist there? I mean, are they significantly different?
No.
Are they absolutely the same?
Well, I mean, everything is the same as, you know, categories over Z, but actually, in my case, everything is defined over FP. So in this case, the scheme and its Frobenius twist are just as isomorphic as schemes over F. So it's not a huge twist. All right, so the second part is about equivalences in T structures. And I need to introduce another algebra, which is now, well, another kind of structure, which is now going to be somewhat less clear. And I'm not going to give too many details about it, and it's called NC Springer. Well, the full name is non-commutative Springer resolution. And this is due to Bezrukavnikov. So that's something which I need to first tell you what happens with default T structures here, and also to actually give proofs of these results. So what is this about? I'm going to have a certain object that I'm going to denote by T, and what it is, it's a G equivariant vector bundle on G tilde, which I'm not going to define, but I'm going to tell you something about it. More precisely, I'm going to tell you something about a related vector bundle, which I will call T0. And that's just the restriction of T to N tilde. So N tilde just naturally sits inside of G tilde. So let me explain some property of T tilde, and with some experience and some insights, you can actually convert this property into a definition or a characterization of this, which is what was done in the Bezrukavnikov-Mirkovich papers. And I'll start to formulate this property from somewhat afar. So let me consider the d of b. And that's going to be a sheaf of differential operators on B, the Plaque variety. Okay? Now, since we are in characteristic P, this fellow here can be viewed as a coherent sheaf of algebras on the Frobenius twist of n tilde. Essentially, the statement about what the center of the sheaf of algebras is. So this dB is the coherent sheaf of algebras on the Frobenius twist of n tilde. And moreover, it's so-called sheaf of Azumai algebras. Azumai algebras is kind of algebras which locally look like matrix algebras. Or in the language of algebraic geometry, they will, in some sense, locally look like endomorphisms of a vector bundle. If you do have endomorphisms of a vector bundle, this Azumai algebra is used as trivial and is called split. Well, this one is not split. It's a nice exercise to understand why. However, if I'm willing to shrink this variety a bit, well, more than a bit, then it's going to split. So how do I need to shrink? I'm going to introduce n tilde 1 wedge. It's going to be the following. It's a spectrum of functions of, well, formal power series on G1 times G1 is n tilde 1. And this beast may look frightening. In fact, you shouldn't be afraid, because what it is just a small neighborhood of B twisted by 1, the 0 section inside of n tilde, which is its cotangent bundle. And then I can just restrict this dB to the small neighborhood. And it turns out that it splits. It's now isomorphic to endomorphism algebra of some vector bundle. So V is a vector bundle on n tilde 1 wedge. And then comes the part about this T0. So if you choose this vector bundle carefully, it has the same indecomposable summons as T0, well, twisted by 1, and again restricted to the same small neighborhood. Okay. So in particular, if I want the endomorphism sheaf of this T0, it's going to look like the sheaf of differential operators, at least on this small neighborhood. Okay. But actually, this sheaf lives on the entire nilpotent cone. and moreover can be extended to the Grothendieck resolution. Other questions? So you can think about it as follows. So you take this, so I don't need to mention this T0 at all. Take this sheaf. It's going to split on this bit weird scheme. And you take a suitable splitting bundle. Then it so turns out that I can extend this bundle to the entire scheme n tilde, listed by 1. And this is how I get T0. Well, I mean, you can get T by an analogous property, but it's more technical. All right. So another thing that I'm going to need is the localization theorem due to Bezrukovnikov, Mirkovich, and Ruminin. And what it says is that the derived global system function, or gamma, going from dB for the differential operators to dB U0 mod is actually an equivalence.
Ivan, so you weren't really saying that V extends, but you're saying that as it's saying when you compose with the sum and it's not V extends, or
And so extends as well.
so it also extends.
Yeah.
Each sum and
So somehow the truth that I'm of course not telling you is that one advantage of this T is that it exists in all characteristics. It's defined over some finite localization of the integers. And so as such, it's going to have some fixed ranks of indecomposable summands. And then V's are going to have these ranks which somehow depend on P.
each indecomposable sum and extends to the whole.
Yeah.
T.
Okay. So now I'm going to state some consequences of this property and of this theorem. For which I will need to introduce a bit more notation. We're going to have A, which is global endomorphisms of T tilde. So T tilde is a sheaf on G tilde, and therefore this is going to be an algebra. It's an algebra over what? Over functions on G tilde. And the functions on G tilde is the same as functions on G times H over H mod W. And then it comes with an action of G. Okay? So that's one algebra that I'm going to care about. And I'm going to care about the algebra A0, which is endomorphisms of T0. And with a bit of work, you can show that it's the same as A tensor over f of h with f0. So I just set variables from h to be equal to 0 here. Okay. And both these guys are known as non-commutative Springer resolution. And in a minute, I'm going to explain why. So they are non-commutative Springer resolutions of well, this is a non-commutative Springer resolution of the nilpotent cone. This is a non-commutative Springer resolution of this. So why do we call them this way? It's because the derived categories are actually equivalent to categories of coherent sheaves on G tilde and N tilde. So let me state the corresponding result. So equivalence number 1, I can consider the functor. Yeah, I think that's correct. So the functor will be R gamma T tensor with something, it's going to go from dB Koch of G tilde. So what happens here, I take a coherent sheaf on G tilde, or complex of such, I tensor with this vector bundle T, and then I take derived global sections. So this is going to land in dB of A mod. It turns out that this is an equivalence. Okay? And that's exactly why we call this a non-commutative resolution. So I just change some T, I change the T structure on derived category of this. Now let's recall that T is a G equivariant vector bundle. Therefore, from here I can, for free, get equivalence between categories of G equivariant objects on both sides. So part 2 is that the same functor is equivalence between well, weakly equivariant derived categories. So how do you roughly prove such things? Well, you just use that property about indecomposable summons and use this equivalence. And then with a little bit of a formal game, you deduce that this must be an equivalence. Now I want to use this 1 and 2 to produce more elaborate derived equivalents, which are the ones that I actually need. And so here's the first one. So it's going to be a functor from dB Koch G Steinberg. That's the category that I care about from the very beginning. To the following category. dBA tensor over FG is A0 opposite mod G. It's going to be given like this. So it's still our gamma of some test sheaf. Tensor with what? Tensor with T, tensor T0 dual, restricted to the Steinberg. Okay. So what the hell is written here? So so what is Steinberg? It's G tilde times N tilde over G. Well, let's forget the subscript G. Then what do I have? Here I will have G tilde times N tilde. Here I will have A tensor A0 opposite. Okay. And here I won't restrict to Steinberg. And so essentially what I'm going to get is an analog of these two equivalences. Okay? It turns out that T dual and T are just as good. They're equally good. Okay?
Sorry, when you said consequences, you were saying that these 1 and 2 are a consequence of localization too.
Yeah, and the properties that I used to characterize the vector bundle T. Well, here, okay, there will be consequences if I have T0 here. Okay? T0 here and tilde and A0. BMR had another version of localization theorem for G tilde, and it's more technical, so I'm not going to mention it. Okay. So now this FG and subscript G that I have here, they correspond to each other. So you can sort of take the previous equivalence without this, okay, and somehow restrict it to this fiber product. There is a little bit of work involved, but that's more or less how it works. And now with this derived equivalence, what I'm going to get a T structure on this category. I'm going to give it another T structure. Which I'm going to call bimodule T structure. Okay, because this is a category of bimodules. So that's one of the T structures that I'm going to care about. So those who successfully survived derived equivalence number 3 can get to derived equivalence number 4, which will require yet a bit more notation. I'm going to write pi for the Springer resolution map from n tilde to G, and I'm going to write PR1 for the projection map from the Steinberg to G tilde. Okay. And then I'm going to do the following. So A is an algebra over here. Okay. So what I can do, I can pull it back under this morphism. What I'm going to get is I star of A, which is a G equivariant coherent sheaf of algebras on n tilde. And I can look at the category of G equivariant coherent sheaves over this coherent sheaf of algebras. Right? So that's another category that I care about. And I want to produce a functor. It's going to go, as usual, from dB Koch G of Steinberg to dB of this category. Okay. How is it going to be defined? Well, all these functors have the same nature. So previous one had argammas, but here I sort of want to pass to something affine in the first coordinate, in the G tilde coordinate, but I want to leave n tilde untouched. So instead of taking derived global sections, I will take the derived push forward under projection 1. And then I only need to deal with the first coordinate, so I take my T, I tensor it with the structure sheaf, and I restrict it to Steinberg, and I tensor. Okay. So that's a functor. Well, I mean, all these functors are equivalences, in fact. So this is an equivalence. And this again gives me a T structure on dB Koch of Steinberg. It now has many names. I'm going to call it stabilized T structure.
Sorry. What is your O in this function?
Structure sheaf.
Okay.
So I get a T structure on dB Koch G of Steinberg. And I'm going to call it stabilized T structure. And it's kind of stabilized compared to this, in some sense. It has other names. It has a name of new T structure. It has a name of Frenkel-Gaitzgori T structure. But I prefer to use this. So it's a new name for a new T structure, okay? All right. Other questions?
When you say T structure, what do you say?
So if you have a derived category of an abelian category, you have this abelian category sitting inside. And as we know, a derived category is a special case of triangulated category. And then you ask yourself, what is the structure of triangulated category that I would need to extract an abelian category from inside of it in such a way that if I deal with dB of some abelian category, I get this abelian category back. It's called a T-structure. It's a collection of two full subcategories that you should think about as a category of objects without positive homology and the category of objects without negative homology. So usually, triangulated category is not the derived category of the heart of the T-structure. So the heart is objects without non-zero homology. But in many situations, particularly in all situations, in this talk, it's going to be the case. So I'm just, you can think about it in this way. I'm finding a bunch of abelian categories for which this one is going to be a derived category.
Sorry, so are you thinking of this as somehow in between the bimodule one, which is kind of purely algebraic, and the original one?
Yeah, that's exactly the case. All right. Now I'm going to, so I still think I have like 15 minutes. Let me state the main results and then tell you something about the proofs. And the main result is the following theorem due to myself earlier this year is that so the category HC U0 is equivalent to that category of bimodules on top, to the heart of the bimodule T structure. But of course I need to twist everything by one, by Frobenius. And the principal block of category O is equivalent to the heart of the stabilized T structure. Again, Frobenius twisted. And it's actually this abelian equivalences which are being proved. Then they imply derived equivalence thanks to this consequences. I should mention another T structure, which I'm not going to define, because it's strictly not suitable for modern talks. So that's going to have a status of side remark. We have this category, this derived category over here. It has so-called perverse T structure. Comes from work of Delin and then Rinkin Bedrukavnikov. Let me call this perverse bimodule T structure. I'm not going to define it. But as every T structure, it has a heart, which is big and important. And so its heart is equivalent to one of the following categories, which are, well, I mean, so let me give it a name and then tell you briefly about what it is. So it's a negative modular affine category O, well, rather principal block of this. And so that's the highest weight category, and highest weight category can be understood by knowing what its tilting objects are. So its tilting objects Sorgel modules. If you were to do the thing in characteristic 0, then here you would get a principal block of negative level affine category O. The same has sense in positive characteristic, and this fellow, as mentioned here, was defined by Ben Elias and myself in 2017. However, you can view this category more geometrically.
Sorry, what did you say was due to Ben Elias? And
The definition of this category. We spelled out what exactly you need to do to Sorgel bimodules to get to this category. What kind of match that you need to do, what you need to do. Now, the work of Bezrukavnikov and Risch in progress identifies this heart with Ivachor reconstructible pair with shifts on the affine flag parameter. Okay. So in characteristic 0, this would be an abelian version of Bezrukavnikov's two realization theorem. And I should say that kind of a big chunk of this equivalence is based on a previous work of Bezrukavnikov and Risch, relating Sorgel bimodules to Harish-Chandra bimodules. Okay, so that was a side remark. It's not necessary to understand the rest of the talk. It's an interesting thing. It should be mentioned. Okay, good. So let me try to tell you how. I think I have time for number 1. Let me try to tell you how number 1 is proved. Number 1 in this theorem. Right, so the first step that you want to do, you want to enlarge your categories which means kind of include them as full subcategories into something. So let me explain what the something is. So a classical fact about universal enveloping algebras in positive characteristics is that they have p-centers. Well, I completely ignored difference between G and G dual. Let me continue with that. So the polynomials on G twisted by 1 embeds into the universal enveloping algebra as a central subalgebra. And if you take a Harish-Chandra bimodule, then the actions of this p-center on this Harish-Chandra bimodule coincide. Okay? That's a fact that you can prove. And therefore, my category of Harish-Chandra bimodules, it is a full subcategory in the following gadget. I take U tensor with U0 opposite. over the P center mod G. So I forgot the Harish-Chandra condition. I only remember that the two actions of the P center coincide. Okay. The enlargement of this category is very similar. I observe that G surjects into G1 by the Frobenius, and therefore, instead of G1 equivariant objects, I can consider G equivariant objects. So I have that this category of bimodules. Well, everything is Frobenius twisted. This is a full subcategory inside, well, the same gadget, but equivariant with respect to G. Okay. So that's step one. Now, step two will be to prove that the enlarged category is actually equivalent. So how can we prove that? Well, first of all, I'm going to prove that they are derived equivalent. So let me give them a name. Let me call this fellow number 1, and let me call this fellow number 2. Okay. And then what do I want to prove? I want to prove that dB of 1 is equivalent to dB of 2. We're going to do it via an intermediate category, which is going to be dB Koch G Steinberg 1. Okay? So Steinberg is twisted by 1, but G is not. And so I have this equivalence and this equivalence. Why do I have this equivalence? This is essentially the BMR localization theorem, and this is a very close relative of number 3. So that I change the groups doesn't really matter. And so now I have this composed equivalence here, and I claim that it's T exact to preserve the T structures. Why is it T exact? It actually follows from that the thing which was called property of the bundle T. How is this relevant? Well, you can check exactness by restricting to this kind of small neighborhood of zero fiber. The small neighborhood of zero and well, this is given by a functor like so, and the bundles that you use, bundles that you tensor with, they just have the same indecomposable summates. It just comes from some Morita field. Okay? And it may be already clear what is step 3. So what do I have? I have this U tensor G1 U0 op G. It's equivalent to the bimodule category. This is step number 2. Now here sits my HCU0, while here sits the very similar category, but G1 equivariant objects. Prove that this restricts to an equivalence. So somehow somehow here the strong equivariance condition is not present. Here it's imposed. Here I just want equivariance with respect to G, and here I want equivariance with respect to its quotient. So it turns out that passing from weak equivariance to strong equivariance on this side amounts to passing from G equivariance to G1 equivariance on this side. So that's how number 1 is proved. All right. Yeah, so I think my time is up, so let me stop.